Welcome! In this elementary calculus tutorial, we are going to find antiderivatives, and that is to integrate various functions. And so once we are finished with that, we will do some numerical integrations, much like what you see in the image above on the left. And so we'll do trapezoidal rule and Simpson's rule. Okay, let's begin with the description of an antiderivative. So we seek a function uppercase f of x such that it is the antiderivative of this lowercase f of x. Now, equivalently, the first derivative of uppercase f of x is equal to lowercase f. Okay, so let's see some examples here in question 1. So in question 1, we're asked to find the antiderivative or integral of 2x. Now, the basic rule here is because we have a polynomial, what we do is we add 1 to the exponent. So we have x to the power of 1 plus 1. And then I divide by the new exponent. So we have this, and then we have a constant of integration. So we put plus c. All right, now let's simplify this. 1 plus 1 is 2. So we have 2 over 2 is 1. X to the power of 2 plus c. All right, now this is our uppercase f of f. This is our antiderivative of 2x. Now notice, if we differentiate this, what do we get? Well, we get the derivative of x squared is 2x, and the derivative of c is 0. So we've got 2x. We have exactly what's inside there. Okay, so let's do question 2. So we've got to integrate 5x to the 4th with respect to x. Now, it's a polynomial, so we add 1 to the exponent and we divide by the new exponent. 4 plus 1 is 5, and then we divide by that new exponent. Don't forget the plus c. Okay, simplifying this, 5 over 5 is 1, so we just have x to the 5th plus c. All right, notice that the derivative of x to the 5th plus c is 5x to the 4th. Okay, let's move on to question 3. Where we're asked to calculate the integral of 0.6 y to the power of 5 with respect to y. All right, now 0.6, that's 3 over 5. So 6/10, which reduces to 3/5. Now we add 1 to this exponent 5. So we get y to the power of 6. Now we're dividing 0.6 by the new exponent 6. And so 0.6 over 6 is 0.1, which we could write as 1/10 y to the power of 6 plus c. All right, let's move on to question 4. So we're asked to integrate 4 over the square root of x with respect to x. All right, now we want to rewrite our lowercase f of x in here so that we put that square root up into the numerator and change that square root into x to the half. So in other words, let's write this 4x to the minus a half. Okay, now since this minus a half is not equal to minus 1, we add 1 to the exponent. So we have 1 minus a half, and then we divide by that new exponent, and we add c. Okay, 1 minus a half is a half. So we have 4 over a half, x to the power of a half, and then plus c. Now we can simplify this. So if we multiply top and bottom of this fraction coefficient here by 2, we've got 4 times 2 over 1/2 times 2, and so that's 8. So 8x to the 1/2, but x to the 1/2 is the square root of x, which is perhaps more familiar to some of you than x to the 1/2. So this is our integral of 4 over the square root of x. Okay, let's do question 5. So in question 5, we have a simple polynomial to integrate with respect to x. Okay, and so the integral of 1 is just x. The integral of minus 3x is minus 3x to the power 1 plus 1 is 2 all over 2. And then we add a plus c. Now, did I do that in the last one? I think so, but let me know if I forgot. Yeah, looks like it. Okay, good. Now let's simplify this. Well, there's nothing really to simplify, is there? So we're done with that one. Okay, let's do question 6. So question 6, we integrate x times x minus 2 to the power of 2 dx. All right, now we've got a product of 2 functions here. So we can do this one in a couple of ways. Perhaps the easiest for you, if you don't know any of the integration rules, is to expand that and then integrate. Okay, so let's do that method first, and then we'll see whether we can do a substitution. And actually, I don't really know whether a substitution will work, so maybe. We'll see. All right, so let's expand this first. Okay, so if we expand x minus 2 all squared, then we have x to the power of 2, but then if we multiply in another x, we've got x to the power of 3. And then the middle term of the square is minus 4, 2 times 2, x to the power of 1, but then we multiply in another 1, and so we get minus 4x squared. Okay, squaring minus 2, we have plus 4, but then we multiply by x, so we have plus 4x. So all we have done here is expanded that expression. Okay, so now let's integrate this resulting polynomial. So we add 1 to the exponent of 3, divide by the new exponent, so we have a quarter, x to the power of 4, and then minus 4 over 3, x to the power of 3, and then plus 4 over 2, x to the power of 2, and then we have plus c. So the only thing really here to simplify is the 4 over 2, which is 2. So we can say that this is 1/4 x to the 4th minus 4/3 x cubed plus 2x squared plus c. Okay, and there's our integral. But let's see whether we can do this one also by substitution. Okay, so now let's say let, and we'll say via substitution, let u be equal to x minus 2. Okay, and so then we would have the integral of x times u squared with respect to x. Okay, and so then what you would do is differentiate this. So du on dx, well, that's just equal to 1. And so if we were to replace that dx, what we would be doing is replacing the dx with du because of this relationship. So what I'm doing here is I'm multiplying both sides by dx, pretending that this is a fraction for a moment. It is not a fraction, but the rules behave in that way. And so at that point, I would put in the du, but then I would see, oh, this doesn't work because I have not been able to eliminate that x. Okay, so this won't work. So let's move on then to question 7. Okay, question 7. Calculate the integral of x to the 1/3, which is the cube root of x, incidentally, plus x to the 1/5, or the 5th root of x, plus x to the minus 1/7. Okay, so we just add 1 to each of these exponents. So 1/3 plus 1 is 4/3, and then we have to divide by that new exponent. So 1 over 4/3, x to the power of 4/3. And similarly, 1 plus 1/5 is 6/5. So we need to divide by that 6/5. And then over here, 1 plus minus 1/7 is 6 over 7. And so we need to divide by 6 over 7 as well. And then we need a plus c. Okay, so we need to simplify these by inverting these fractions in the denominator. So what we're doing here is multiplying top and bottom in this first one by 3/4 so that that denominator cancels to give 1. So we've got 3/4 x to the power of 4/3 plus 5 over 6, x to the power of 6 over 5, and then plus 7 over 6, x to the power of 6/7, and then plus c. Okay, fantastic. Let's move on to question 8. Let me make my face clear. Hopefully that went into focus. Hello, hello. Okay. All right, question 8. Find y in terms of x. Well, we're given dy on dx equals 8x plus 1. And it goes through, so we'll just say contains the point minus 1, 4. Okay, so this is a differential equation, but it's very easy to solve. So integrating both sides with respect to x, we have y as a function of x is equal to the integral of 8x plus 1 with respect to x. And so let's integrate this now. Adding 1 to the exponent x, we have 8 over 2 x to the power of 2, and then plus x, and then plus c. Okay, so fantastic. Let's simplify that. 8 over 2. And so y as a function of x is equal to 4x squared plus x plus c. Now, since it contains this point minus 1, 4, well, we can use that subbing in here to find out what c is. All right, so let's do that now. So 4 is equal to y of minus 1, which is 4 times minus 1 squared plus minus 1 plus c. Okay, simplifying this, we have 4 equals 4 for 4 times 1 minus 1 plus c. So canceling the 4's on both sides by subtracting 4 from both sides, and let's add 1 to both sides, then we get c has to be equal to 1. All right, so c is 1. Now we see, well, y as a function of x is equal to 4x squared plus x plus 1. Okay, let's move on to question 9. Says, is 3x squared integrated with respect to x equal to x cubed? Well, that's only one possibility, right? Because there are infinitely many functions, uppercase f, that satisfy integral equal to that, right? So let's integrate this. And the short answer is no, right? It's not always equal to that. So 3x squared integrated, this gives us, remember, we add 1 to the exponent and divide by the new exponent. And so that exponent is 3, and then we have plus c. And so we get x cubed plus c. So the answer is, in general, no. So I'll just write not in general. All right, moving on, and I'm sorry if you couldn't quite see those questions. Maybe you could hear me. Find the approximate area under the curve of the equation y is equal to 2x plus 1 by dividing up the indicated intervals into n subintervals, and then adding up the areas of the inscribed rectangles. Okay, so the first thing we need to do is draw a pretty good picture. All right, so when x is equal to 0, we have y equals 1, so we have a point there, and then we have a slope of 2, so we have another point, 1, 3, and so our line comes up through here. Now it says area under the curve. Well, what are the boundaries here? From 0 to 2, okay? From 0 to 2, and so then up here we'll have another point, 2, 5. All right, and so we seek the area under this line. All right, now it says divided into 4, so that would be with a step size of 0.5 in this case, because the endpoint's 2 minus 0 over 4 is 2 over 4, which is a half, but let's call it 0.5. So we have a step size of 0.5 here. Let's label the 0 and the 2. Okay, and so we're asked to, we are inscribing rectangles, and so we draw little rectangles here at each of these steps. So then what we need to know is, what are all these points here that meet the curve? All right, what are these points? Okay, so let's say 1 is here, 0.5 here, and then 1.5 here. So these are the x values, so we need to know the y values at those points. Okay, and so y of 0.5 is equal to 2 times 0.5, which is 1 plus 1, and that's 2. So the height here is 2. Y of 1 is equal to 2 plus 1, which is 3. So this will be 3. And then up here we need this as well. So y of 1.5 is 3 over 2. So 2 times 3 over 2 is 3, and then we add 1, and so we get 4. So this has height 4. All right, and so we don't need the last one because these are inscribed and we stop when x is 2. So let's shade our area to make it really clear what we're up to. Okay, and so the area, let's say the first area segment, A1, is equal to 0.5 multiplied by the height of this spot right here. So we need then y of 0 is 1, and that is our height here. So the height is 1. All right, and so this adds up to 0.5. All right, now the second area segment is equal to 0.5. That's the width, and then the height is 2. And so this is equal to 1/2 of 2, which is 1. All right, for the third rectangle, the area is equal to 0.5 multiplied by the height, which is 3. And so half of 3 is 1.5, or 3 over 2. And then the area of the fourth rectangle has width 0.5, and then we multiply by the height, which in this case is 4. So that's half of 4, which is 2. All right, now the sum of the areas of those rectangles, so A1 plus A2 plus A3 plus A4, so this is 0.5 plus 1 plus another 1.5, so 1.5 plus 1.5 is 3, and then plus another 2, that gives us 5. All right, so we have completed part A there. Now in part B, well, this will take a little bit of time and would be boring to watch me do it, so let's get some computer help here, but you can do this by hand yourself. All right, and so what I'm going to do is get Mathematica to do this, but I'm going to do it mostly as a by hand calculation so you can follow along with your calculator. All right, so part B, here we have n is equal to 10, and so the step size delta x is then 0.2. Now note that that is 2 minus 0, so for the endpoints, the difference of the endpoints, divided by 10, and that's 2 over 10, which is 0.2. So that's how they get the 0.2 there. All right, so this is the width of our rectangle when we add these up. Now let's just do the first one by hand. So A1 would be equal to 0.2 multiplied by, now these are inscribed, and so multiplied by y of 0. Okay, and then y of 0, remember that's 1, right? That's 1. So we have 0.2 times 1. Okay, now the second one, A2, in this case, would be 0.2 times y of 0 plus 1 times 0.2. Okay, and so I write it this way for a reason so that I can get the computer to automate this in a moment. So we have 0.2 times y of 0.2, and now y of 0.2 is 0.4 plus 1, or 1.4. Okay, so we have 0.2 times 1.4. So twice 1.4 is 2.8. If I divide that by 10, I have 0.28. All right, now at this point, I'm ready to get the machine to help me out with the rest. So first, I'll build a function, y as a function of x. All right, just to make this more convenient. All right, what is that function? Well, it's just 2 times x plus 1. Okay, simple. Now what I want to do is evaluate 0.2 times y of 0, just to confirm that I should get 0.2 for that. Yes, I get 0.2. All right, now what we want to do is put in 0 plus 1 times 0.2. Okay, I get 0.28. That agrees with my hand calculation. So now I am ready to replace that one with a j and make a list of these by writing table. Tabulating this as j goes from 0 up to 9, because that would give us 10 rectangles. All right, so now you see I have a list of the areas of those 10 rectangles. Now the first two agree with what we got by pen and paper, so now we just have to add all of these up. Okay, so to do that, I'm going to replace the word table with sum, which would add them all up. And so the sum of all of the a subscript j's, as j goes from 0 to 9, well, this is 5.6, right? And so this is presumably a better estimate of the area under this line from 0 to 2 than what we got with larger step sizes of 0.5, right? So this will be better in getting 5.6. All right, so now that we have that, let's do question 11, which is to calculate the actual area under the curve between 0 and 3. And now this is what's called a definite integral. So we integrate 2x plus 1 with respect to x, but we have boundaries. Now I see it says 0 and 3, so I'm going to change that to agree with what we have above. I'm going to change it to 0 to 2, and then we can also do 0 to 3. Okay, so what we do first is we integrate, finding an antiderivative of 2x plus 1. So we add 1 to this exponent, x, divide by the new exponent, and so we get x squared for that. Integrating 1, we have x. And now I like to put square brackets around this and then rewrite the bounds, the bounds of my integration there on the right hand side. But some people just like to write one vertical line on the right hand side. That's fine too. Okay, now what we do next is we sub in the 2 into our function here, sub in the 0 into our function, and take the difference of the 2. So in other words, 2 squared plus 2 subtract 0 squared plus 0. Okay, and so what are we going to get? 4 plus 2 is 6, minus 0 is 6. So we get 6, and that is the exact area under the curve from 0 to 2. Okay, let's do question 11 as it was written. And I'm sure this is a typo here. I meant to have a 2 for my bounds of integration, but we'll do this because it's typed there. Okay, so now what we would do is sub in the 3 rather than the 2. And so in this case, we would get 3 squared is 9 plus 3 minus 0, because when we sub in the 0 here like this, we're subtracting 0. And so for that integral, we would get 12. All right, but in particular, the 6 is a better estimate of the area under the curve between 0 and 2 than 5.6 is. Right, so this is an underestimate because, remember, we've inscribed our rectangles. Right, and so what we're missing in these calculations is all the area in these little triangles above it. All right, let's move on now to question 12. Find the approximate area under the curve of the equation y equals 9 minus x squared by dividing the indicated intervals into n subintervals and then adding up the areas of the inscribed rectangles. Okay, and now this is for x equals 2 to x equals 3. So we're estimating the integral from 2 to 3 of 9 minus x squared with respect to x. And so we're doing so with the trapezoidal rule. Or not quite the trapezoidal rule, is it? Because we are inscribing rectangles. Okay, so now what we need to do is evaluate the function, but let's get a nice picture of this first, which I have already done for us here, I think. Let's see. I'll run this just to make sure. Come on. Okay, so yes, I've just run that, and this is what that looks like. And this looks like this one is done in terms of 1, 2, 3, 4, 5, 6, 7, 8, 9, and then there's an empty rectangle here at the bottom, it looks like. So 10 rectangles. So this is basically looking at part B of the question. Okay, so let's draw a picture. So it's something like this, right? Here we've got x is 3, and then in here, starting at x is 2. Okay, now if we divide this up in the difference of 3 minus 2 into 5 parts, we have delta x is 0.2, just as given there. So let's attempt to separate this into 5 parts, 3, 4, 5, okay, something like this. And so these are inscribed. And incidentally, the picture really helps you think about this. Okay, now we need to know where these points are. This, and this point. Where are these? So the first one occurs when x is 2.2, and then we have 2.4, 2.6, 2.8, and 3. So these are x values of those points. So the y value is gotten by subbing in these numbers into the function. Okay, so let's do this somewhat by hand. Y of 2.2 is equal to 9 minus 2.2 squared. All right, I will get the machine to calculate that. So 2.2 to the power of 2 is 4.84. So 9 minus 4.84. Okay, so what do we get? So for that one, we get 4.16. All right, let's do our next y value. So y of 2.4. So just change the 2.2 to 2.4. So we now have 3.24. Okay, now let's do this at 2.6. So we get 2.24 now at 2.6. Now 2.8, what does this give us? 1.16. Okay, next at 3.0, we have 0. Okay, so now completing the calculation of the area, which is this shaded region that I'm shading right now. And then there's nothing to shade there at the bottom. So we need to add these up, multiplied by the width, which is 0.2. All right, so the first area, A1, which will be this one here. So A1 is 0.2 multiplied by 4.16. Okay, so I'll calculate that. 0.2 times 4.16. So we get 0.832. Now the next one, 0.2 multiplied by 3.24. So for this, A2 we have 0.648. Okay, now A3, which is the area of this third one, so A3 is 0.2 multiplied by 2.24, and so 0.448. And then A4, 0.2 times 1.16. And so we have 0.232. Okay, last one, A5. Of course, that's 0.2 times 0, which is 0. And now the sum of these 5 numbers, let's add them up. So we have 0.832 plus 0.648 plus 0.448 plus 0.232 and then plus 0. Okay, so the sum of all these is equal to 2.16. All right, and that should be an approximation of the integral from 2 to 3 of 9 minus x squared with respect to x. Okay, next we are asked to break this up into steps of 0.1 rather than steps of 0.2 and then repeat the procedure. All right, so let's do this like what we did in the previous question. I will change my function here to the function 9 minus x squared. Okay, now the step size here is 0.1. All right, let's have a look at these numbers. Okay, yes, this looks fine to me. And now I want to change that list or table into a sum so I can add all of those areas up. And so we get, I'm just going to put this here in the corner. So we've got with n equals 10, the integral from 2 to 3 of 9 minus x squared was estimated as approximately 8.715. Does that seem right? Maybe. Doesn't seem right to me though, right? Because these two are vastly different. Okay, let's take the actual integral, because Mathematica here will integrate this for us. And then we'll do that by hand in the next question. So 8 over 3, 2.66. So yeah, I must have done something wrong here. All right, let's find out what it is. Oh, I see. Yes. Yes, yes, yes. I've started in the wrong spot. Okay, so I should start at 2 rather than 0. So then we should get 2.915 when we do this properly. All right, so remember you got to start at 2, because that's where we begin that integral there, 2. All right, then I'm adding on 0.1, so 2.1, then we get to 2.2, 2.3, and so on, right? Okay, fantastic. Let's move on then to question 13, which is to do this calculation here, or this one here, by hand. Okay, let's scroll up so you can see the problem. All right, says calculate the definite integral from 2 to 3 of 9 minus x squared dx. So this is the exact area under the curve between 2 and 3. So we integrate 9 minus x squared, and so we get 9x minus 1/3 x cubed, and then we need to evaluate that at 2 and at 3 and take the difference. So we sub in the 3, we sub in the 2, and then we subtract the result. So 9 times 3, and then minus 1/3 of 3 cubed, and then subtract, put in a big bracket here because you're going to subtract what's inside when you sub in 2. So then we have 9 by 2 minus 1/3 of 2 to the power of 3. Okay, let's simplify. We have 27 for 9 times 3. Now 3 cubed is 27. Divide that by 3 and we have 9. So 27 minus 9. And then we are subtracting 18 for 9 times 2. And then minus 8 over 3. Okay, so 8 over 3, that is 2 and 1, and sorry, no, yeah, 2 and 2/3, isn't it? So it's 2 and 2/3. So let's write 27 minus 9 minus 18, and then plus, because minus times minus is plus 2, and then plus 2/3. Okay, good. Now 9 plus 18 is, well, it's 27, isn't it? So these vanish. And so we have 2 plus 2/3, which is 8/3. Or approximately, actually I'll just write 2.6 recurring. Okay, good. And so for the estimates, we got 2. What did we get? 2.1, I thought, but I can't find the page. And 2.91. Okay, let's move on now to question 14. Calculate the definite integral from 0 to 3 of 6x with respect to x. Okay, we add 1 to the exponent. So the new exponent is 2, divide by the new exponent, and add c. So this gives us 3x squared plus c. And we're done with that problem. Okay. Are we? No, we're not, because we have not done this part. Okay. So we have to put the 0 to 3 in. So we sub in the 3. Now we don't really need the plus c here, because it always gets subtracted. So we have 3 times 3 squared. I'll put it in here so you can see what happens. And then 3 times 0 squared, and then plus c. Now if we expand this, the c's vanish. So 3 times 3 squared is 3 cubed, which is 27. 3 times 0 squared is 0, and so we just have 27. Okay, let's move on to question 15. Calculate the definite integral from 0 to 2 of 4x cubed with respect to x. Okay, so now I put my integral in this box. I add 1 to the exponent, I get an exponent of 4. Divide by the new exponent, 4 over 4 is 1. Then we have to substitute in the 2 and the 0. So we have 2 to the power of 4 minus 0 to the power of 4. 2 to the power of 4 is 16, so we have 16. Okay, question 16. Calculate the definite integral from 4 to 9, p to the power of 3 over 2 minus 3 with respect to p. Okay, adding 1 to the exponent, 3 halves plus 1 is 5 halves. 1 over 5 halves is 2/5. Integrating minus 3 gives minus 3p. This is from 4 to 9. Okay, we sub in the 9, we sub in the 4, take a difference. So this is 9 to the power of 5 over 2, and then minus 3 times 9. And then we subtract 2/5, 4 to the power of 5 over 2, minus 3 times 4. All right, simplifying, 9 to the power of 1/2 is the square root of 9, which is 3. So this is 3 to the power of 5. 3 times 9 is 27. Now 4 to the 1/2 is the square root of 4, which is 2. So 2 to the power of 5 there. So minus 2/5 times 2 to the power of 5, and then plus 12 because we have two minus signs. All right, let's simplify this. So 3 to the power of 4 should be 9 times 9, which is 81. And then 81 times 3 is at 243. I better get on the machine. 3 to the power of 5. Yep, 243. So 243 minus 27. And then over here, 2 to the power of 5 is 32. 32 times 2 is 64. So minus 64 over 5 and plus 12. Okay, let's confirm. Yes, okay. Then I'm multiplying that by 2 and then dividing the result by 5. Minus 64 over 5. Okay, so 2, 4, 3. Minus 27. Minus that fraction. And then plus 12. So we've got 1076 over 5. And you would probably like a numerical estimate of that. So let's replace that 5 with a 5.0. And so we have this equal to 215.2. Okay, let's move on to question 17. Calculate the definite integral from 1.2 to 1.6. 5 plus, this is 6 to the power of x to the minus 4th. 6 times x to the minus 4, I should say. Okay, and so let's integrate this first. So we have 5x. Adding 1 to the exponent minus 4, we get minus 3. So it's plus 6 over minus 3. 1.2 to 1.6. Okay, let's simplify that. So 5x minus 2x to the minus 3. 1.2 to 1.6. So we sub in the 1.6, we sub in the 1.2, we subtract the results. Okay, so I've taken that 3 downstairs and written it as a 1 over x cubed and then sub the 1.6 in. Okay, now let's simplify this. 5 times 1.6 minus 2 over 1.6 to the power of 3. Okay, so for the first one, we have 7.51172 and so on. I'm sure it continues. Now for the second one, we are going to get 4.84259 and so on. Okay, let's subtract the two of these. And so we have 2.66913 and so on. Okay, let's do question 18. Calculate the definite integral from 1 to 2 of 3x to the 5th minus 2x cubed dx. All right, adding 1 to the 5 gives us x to the power of 6. So 3 over 6 is 1/2. Add 1 to the 3, you get 4. 2 over 4 is 1/2. Now we need to sub in the 2 and sub in the 1 and subtract. I'm going to factor out the 1/2 out of the whole thing first. So 2 to the power of 6 minus 2 to the power of 4. 1 to the power of 6 minus 1 to the power of 4. Okay, now this obviously gives us 1 minus 1, which is 0. So we really need to calculate this one. Now I can see there's a common 2 to the power of 4 to factor out the front of this. So I don't need to calculate each of those powers. So I can write this as, so factoring the 2 to the 4th out, we have 2 to the 4th over 2 is 2 to the power of 3. And then what remains here is 2 to the power of 2 minus 1. Okay, so we have 8 times 3 is 24. All right, next one, we're going to use the trapezoidal rule. All right, so we're calculating the approximate area. And so let's do this exactly first. Okay, and so subbing the 1 in, we've got 1 minus 1/3. And so we're supposed to get 2/3. All right, now to do this via the trapezoidal rule, the trapezoidal rule says that this area from 0 to 1 of 1 minus x squared dx is approximately the change in x. So if we have n equal to 3 and we have 0 to 1, so this is 1/3 is our step size, right? So then we have 1/3 multiplied by 1/2 the first one, which is f of 0, and then 1/2 of the last one, so f of 1, and then we add up each of the function evaluations at the other points. So we have 1/3 and we have 2/3 are the other points. So plus f of 1/3 and f of 2/3. Okay, now it's 1/2 the first one plus 1/2 the last one plus the sum of all the other function evaluations. And so if you were to expand this summation here, that's what you would get, because some of these appear twice. All right, so let's evaluate this now. So here, f of x is 1 minus x squared. So f of 0 is just 1. So we have 1/2 of 1. And then f of 1 is 0. And then f of 1/3 is 1 minus 1/9. F of 2/3 is 1 minus 4/9. Okay, let's simplify this. So 1/3 times 1/2 plus 8 over 9 plus 5 over 9. Okay, and so if we put this all over 18, 1/3, this is 9 over 18, 16 over 18, and 10 over 18. Okay, 9 plus 16 is 25, plus 10 is 35, so 35 over 18. And then 3 times 18 is 30 plus 24, which is 54. Okay, so we need to calculate a numerical estimate of this. That'd be convenient. And so I get approximately 0.648148 and so on. Okay, which is not too far away from the 2/3 that we got in the exact calculation. All right, let's move on to question 20. Approximate the value of the integral from 3 to 8 of the square root of 1 plus x with respect to x by use of the trapezoidal rule with n equal to 5. Let's make a quick plot of this function first. Okay, it's slightly curved, it looks like. And increasing in this range. So use the trapezoidal rule with n equals 5. All right, so what we need to do here is take the difference. So 8 minus 3 is 5. Divide this by 5. So we have a step size of 1. This is our delta x. All right, so redrawing this picture. So when x is 0, we have 1. When x is 1, we have the square root of 2, which is 1.4 or so. When x is 2, we have root 3. When x is 3, we have the square root of 4, which is 2. So then we would have 2 up here, and so on and so on. But we start this at 2. And so we're also interested in the function evaluation at 8. So when x is 8, we have the square root of 8 is 3. So the height here is 3. Okay, and so using the trapezoidal rule, the integral from 3 to 8 of the square root of 1 plus x with respect to x is equal to 1/2 f of 3 plus 1/2 f of 8, and then plus the sum of all the function evaluations everywhere else in between in steps of 1. All right, and then that all gets multiplied by delta x. So 1 outside of all of this, but inside here we have f of 4, f of 5, f of 6, and f of 7. Okay, where f of x is equal to the square root of 1 plus x. All right, so let's simplify this. And this should say approximate here, not equals. Approximately equal to this. All right, so f of 3. Now f of 3 is 1/2 of the square root of 4. So 1/2 of 2 is 1. Okay, 1/2 of f of 8. 8 plus 1 is 9. The square root of 9 is 3. So 3 over 2 is 1.5. And then f of 4 is the square root of 5. F of 5 is the square root of 6. F of 6 is the square root of 7. And f of 7 is the square root of 8. All right, so this is our approximate area. Now we need to simplify this. Well, I mean, look, we can actually give an exact value, right? Because this is an exact value. So 2.5 is 5 over 2. But in order to compare with an exact value of the definite integral, let's take a numerical estimate of this. So we want then 1 plus 1.5 plus the square root of 5 plus the square root of 6 plus the square root of 7 plus the square root of 8. And so we get approximately 12.6597 or so. All right, now what is the exact value of the integral? Let's just get the computer to do this because you haven't learned integration by substitution yet. So let's say integrate the square root, sqrt, 1 plus x with respect to x. What do we get for this? X plus 1 to the power of 3 over 2. All right, so this is via substitution that you would do this. So I'll say extra the integral 3 to 8 of 1 plus x dx is 2/3 1 plus x to the power of 3 over 2, and we evaluate this from 3 to 8. Okay, so subbing in the 8, we have 2/3. 8 plus 1 is 9. The square root of 9 is 3. So 3 to the power of 3. And then subtract 2/3. 3 plus 1 is 4. The square root of 4 is 2. So 2 to the power of 3. And so we can factorize out a common 2/3. So we have 27 minus 8. 27 minus 8 gives us 19. 19 times 2 is 38. So 38 over 3. Okay, let's estimate that numerically. And so we get 12.6 recurring, which is quite close to this. Okay, last one on the problem set. 21, approximate the integral from 0 to 8 of x to the 1/3 dx using Simpson's rule. All right, now Simpson's rule is slightly more tricky than the trapezoidal rule. So with n equals 2, okay, so we want to draw a picture of this. So let's plot this here. Okay, so we have this. Okay, something like this from 0 to 8. Now, let's see, what is it saying here? N equals 2. So we're dividing this up into 2 parts, it looks like. So that would be 4 there. Okay, and so to use this formula here that we've got for Simpson's rule, with n equals 2, we have 4 minus 0 over 6, and then f of 0 plus 4 times f of the sum of 0 and 4, and then plus f of 4. Okay, and now we need to do this from 4 to 8 as well. So 8 minus 4 over 6. F of 4 plus 4 times f of the sum of 4 and 8 all over 2 plus f of 8. Okay, so we need f of 0, we need f of 4, we need f of 2. So let's make a table here, or a list. F of 0, we need f of 4 over 2 is 2. We need f of 4. In here we have 4 plus 8 is 12. 12 over 2 is 6. And then we need f of 8 to do this. Okay, now the cube root of 8 is 2. The cube root of 0 is 0. So we need to take the cube roots of these numbers and then sub these in here. Okay, moving on, let's simplify this. So 4 over 6 is 2/3. F of 0 is 0. 4 times f of 2 is 4 times 2 to the 1/3. And then f of 4 is 4 to the 1/3. Then we have 8 minus 4 is 4. 4 over 6 is 2/3 again. F of 4 is 4 to the power of 1/3. 4 times f of 6. Okay, and then we have f of 8 is 2. So there's a common 2/3 here. And then we have, hang on, is this right? No, that's 6 to the power of 1/3 here. Okay, good. So let's simplify this. We've got 4 times 2 to the 1/3. Then we have 4 to the 1/3 plus 4 to the 1/3, so plus 2 times 4 to the 1/3. And then we have 4 times 6 to the 1/3, and then plus 2. Okay, let's get an estimate of this. So 2 divided by 3.0. So I make sure that we get a numerical estimate. And then we have 4 times 2 to the power of 1/3 plus 2 times 4 to the power of 1/3 plus 4 times 6 to the power of 1/3 and then plus 2. And so my calculation tells me that this should be 11.6553 and so on. All right, now let's get an exact integral for this one. So to do this exactly, we can do this easily by hand. So 0 to 8, x to the power of 1/3 dx. So we add 1 to the exponent, we get 4/3. Divide by the new exponent, so that puts a 3/4 in front. And then we evaluate this from 0 to 8. And so that is 3/4 of, now 8 to the power of 1/3 is 2. 2 to the power of 4. Okay, which is 16. And then when we sub in 0 here, we just get 0. So this is 16 divided by 4 is 4. 4 times 3 is 12. So we get 12 as our exact area under the curve from 0 to 8, but 11.6553 is pretty close. All right, thank you.